I'm going to rearrange that a little bit, and we have the E field at P. And now the only thing we can really pull out is e to the j omega t minus kr, because now the term E object, the variation, does depend on where you are in the slit. It should stay inside the integral. So we can say integral E of the object, just the pattern of brightness of the object. And then we can write it e to the j. And then it would be, I'm going to write it as kx over r and put the big X on the little x on the outside. So kx over r, x plus k big Y over ry, right? dx dy. dA is just dx dy. So you could write it like that, and now you may recognize this. What is this? That is a Fourier transform. So diffraction, the diffraction pattern in the far field limit is the same function as a Fourier transform. And we didn't quite go this far with Fourier transforms, but let's just think for a minute. We did Fourier series, right? We said if we have a pattern from L to minus L, say a pulse that's sort of at 1 in this region and then 0 everywhere else, we figured out how to make that pulse. We said, well, you can write the sum, infinite sum of sinusoids and give them different amplitudes. And how do you find the amplitude? Well, it's equal to this integral formula, all right? Well, here's a few analogies I can kind of give you. So before we had the interval was, well, it's 2L. But let's let that go to infinity, right? If you do this from minus L to L, you can make a pulse, but then the function you get repeats the pulse over and over. So why not just make the domain infinity and say there is only a pulse at 0 and nowhere else? Well, if you do that, let's see, what is that going to do? Before, when you added up all of the sort of the modes, it was always n pi x over L, right? So x over L, and then 2x over L, and 3x over L. So the spacing was sort of the delta k, the spacing between in frequency was sort of pi x over L. Well, that goes to 0. So instead of thinking of this as a sum of a discrete set of frequencies, it becomes a continuum. So when you make the domain super wide, you get a continuum of frequencies. And that basically means you go from a sum to an integral. Okay? So you don't have to do Fourier series as discrete sums. You can do them as integrals over infinite domains, and then you get something like you can describe a function f of x as the interval for, or the integral from minus infinity to infinity of some other function g of k. Basically a function that describes the spectral components, spectral in terms of 1 over position, of the function f of x of position. Okay? So that would be then e to the minus j k x dk. Right? So you integrate over spatial frequencies of the sort of the spatial spectrum of this function. And then you can also go back. G of k is the integral from minus infinity to infinity of f of x, e to the jkx positive dx, and you need a 2 pi to make it all work out, 1 over 2 pi. Anyway, if we had kept talking about Fourier longer, we would have gotten to this. And this is a Fourier transform. You can take f of x, apply a Fourier transform, and you can find the spectral components g of k. Okay? And that's what's interesting, is that's what light is actually doing. Okay, so if you have some object here, I'll draw that happy face, a little lumpy, and light comes off, the diffraction pattern is actually a Fourier transform of the spatial information in that pattern. Pretty interesting. So I can actually sort of demo this for you. I have our polarization lamp with no polarizer and a piece of paper. So I'm just going to write something, and that'll be our object. So I'll write PHYS 201x MOOC love. Okay, I don't know. Not rehearsed. Okay, so here is our object. So the light coming through the lamp and off those letters, we're getting the diffraction pattern of those letters, and it's actually the Fourier transform of that pattern. So I can show it to you on a camera. So this is just a regular SLR camera, and if I turn it on and put it in the right mode, you have direct access to the sensor. So we're putting that pattern directly onto the sensor. So all that image information is there. So now I'm recording so you can see it. It's basically blank. It's not very exciting. There's some lines going down, that's just the CCD acting funny. So the pattern is there. That really is a diffraction pattern, but all the colors mixed together and all the different areas all overlap and you don't see anything. So the Fourier transform is not interesting. However, what if we were to take another Fourier transform? So a Fourier transform of a Fourier transform gets you back to the original function. So we have the object, we have its Fourier transform coming. The way we can take another one is to diffract again. Okay, so I'm going to take this piece of foil, which is continuous foil. I'm doing all this live, so you know I'm not tricking you with a lens anywhere. So if I cover up the foil over the lens, we see nothing, right? So obviously it's blocking all the light. But I can take a pen and put a small pinhole in the foil, and then our Fourier transform diffracted light will diffract through the hole, and we'll get another Fourier transform, another diffraction. And we'll put it over here, and we'll take the Fourier transform, and we'll take another Fourier transform, and see what we get. And if I block it just right, there it is. Physics 201X. There's the image of there. It's a real live image I can see you right there. All right. So this tells us a little bit about why imaging is not perfect. You've probably heard of a diffraction limited image, right? Or that imaging with light is diffraction limited. And the reason is, if you have some complex object like this, you can actually think of it as a Fourier sum of a bunch of different spatial modulations of the light. So if your complicated object has one spatial component, kx, where it's sort of like 1 over the wavelength of that, then where is the light going to go? It's going to diffract kx. That spatial component will go out at k big X over big R, right? That's the spatial frequency. Right? That's what it'll go out at. So it'll go off like that. And now, if we wanted to solve this and say, where's it going to show up on the plane? Well, then this is big X here, and this is R, and K is really 2 pi over lambda and everything, so we could actually write it as 2 pi, and we could put a lambda up there. But where it's going to go, if we solve for X, how high it's going to go, is going to depend on that spatial frequency. So the higher the spatial frequency, the higher the diffraction angle that the light goes. So the information of a high spatial frequency actually goes off at a very sharp angle. And if your little pinhole is not catching it, if it doesn't see that information, then it doesn't record it. And that sharp spatial frequency will not be in the image. And the image only has the spatial frequencies that fit into the pinhole. But it's not just true for a pinhole. If you have your eyeball here, your eyeball has a limited pupil, right? So it only gets as many spatial frequencies as fit in the pupil. Or if you have a nice big microscope objective, it only captures as big of a spatial frequency as fits in the microscope objective. So optical imaging resolution is always limited because the high spatial frequencies don't diffract into the lens. And if you don't have them in that information, they're not going to end up in the image information. So I want you to realize that as you walk around every day, you're bathed in the Fourier transform of everything around you. I find that a little mind-blowing. And if that doesn't blow your mind, also keep in mind that that Fourier transform is built up of photons, which actually are statistical particles that follow statistical unpredictable paths. If that doesn't blow your mind, keep in mind that what actually goes into your eye and onto your retina is sort of loosely interpreted by your brain. So you're not technically seeing what really hits your retina, right? So hopefully those three things together blow your mind a little bit when you think about imaging.